get started. I think I've told you already that we're going to have our second midterm on a Monday of the 9th week, okay? So this is the 7th week right here. So we're talking about a week from next Monday. Is that right? A week from next Monday. And I'll let you know a little bit later on exactly what will be covered, okay? Huh?
So it's going to be the week before.
So not this.
Not this coming Monday, but a week from next Monday.
Okay,
Yeah.
so the weekend earlier.
The Monday of the 9th week.
It's the Monday
Is that okay?
after,
The week after.
Somebody? Oh, a week?
GR.
Okay. Is that okay? Would
That's
that
fine,
work
that's
out?
fine.
Okay. GR is when? Because I'm going to have my mechanics
Next
on
Monday
the...
is Friday.
Next Monday is GR, Friday is the mechanics,
Yeah,
and
next-
then the Monday is this. So you have a...
We'll be fine.
You'll be fun for you. Okay.
Yeah.
All right. As long as it's okay with you.
Yeah, so next Monday, for us as mechanics, next Monday, the next Wednesday is electronics.
What happens Wednesday? Somebody told me there was an optics
And then
test.
the following Monday after that week.
Yeah, anyway.
Okay, so we're right here.
I don't think any of us
So
are.
not this week,
Not that, the next week.
so two,
This is a 7th week. That's all I know.
so the 23rd.
Yeah.
Okay. Okay, so there's just a little bit on the chapter on the Lorentz group to cover before we move over to something else. Now, originally I had planned for a couple more chapters in groups and group representations, but I do want to get into the geometry part of the course before too long. And so we'll see how far we can go on the geometry part. I plan to talk basically about some basic theory of fiber bundles, and then in particular focus on Riemannian geometry. That will be the part that hopefully will be useful for those of you who are interested in general relativity. And then finally, if there's some time left, I'll come back to group theory, but I suspect probably not, okay? So we're going to go into some general discussion of gauge field theories in physics, and then that as general motivation for the study of the relevant differential geometry that's useful in classical gauge field theories before quantization, as they say. And so that will kind of wrap up the course. Okay. So now, so let's just wrap up some things about a couple more interesting things about a Lorentz group that I want to talk about. Especially the relationship between this group SL2C on the one hand and the orthogonous proper Lorentz group on the other. It turns out technically the SL2C is what's called a universal covering group of the proper orthogonous Lorentz group. I'll just try to explain. Now, just to recap a little bit in here, you see that the group, which is called the Lorentz group, L4, which consists of the group of transformations on Minkowski space, which preserves the length of vectors, 4 vectors in Minkowski space, can be broken up into 4 disconnected parts. Now, I won't prove that, but I just want to note this fact in here. Sort of a brief coverage of the group of the proof of this is given in the text, but even that I don't want to go into too much detail. But I do want you to have this picture in here. This is called L sub 0. Sometimes it's called SO13 up, or sometimes it's called L plus up. Okay, the plus, the sign at the bottom refers to whether the determinant is equal to +1 or -1. And then the arrow up or down points to the value of this particular element of the 4x4 matrix, which is a Lorentz transformation. If this is larger than or equal to 1, we have proof in general that this in here. This one has some special significance in here because it's the one which connects the time to the rest of the coordinates and so on. This one is always either bigger than 1, bigger than or equal to 1, or less than or equal to -1. If it's bigger than or equal to 1, we use an up sign. If it's less than or equal to -1, we use a down sign. And so coupled with the fact that the determinant can be either equal to +1 or -1, we have 4 possibilities, right? So we have this. Now, so this is one of them. The other would be L minus minus up, down. And then finally, there would be this L plus, but down, like that, okay? So this one has determinant +1, this particular element is less than or equal to -1, and so on and so forth. None of these three is a subgroup, although they're all part of the Lorentz, big Lorentz group 4. Only this one is a subgroup because that's where the identity lies, obviously, okay? Because the identity, the determinant of the identity is equal to +1, and the identity is when this thing is equal to 1, okay? So this thing in here is a subgroup of L4. It's called the proper orthogonal Lorentz group. The relationship between SL2C on the one hand and L4 on the other is this, that this is SL2C. By the way, SL2C, of course, is the group of 2 by 2 complex matrices with determinant +1. S refers to the word special, which means that the determinant is equal to +1. Okay? The C in here refers to the fact that the matrix elements are complex numbers in general. Okay? 2 in here refers to the fact that this is a 2 by 2 matrix. So this is the, yeah?
What was the L again?
L? Oh, L is a linear. That means it's a group, so linear means it's a linear group. Each matrix in there has an inverse. Okay? It's invertible matrices. Okay? Okay, now we saw that there's a group homomorphism taking us from this group to this group, but we also mentioned that the image of the homomorphism is just this thing in here, okay? In other words, so there's if this is the identity in here, then the group homomorphism takes the identity from here to the identity in here, and the group homomorphism is such that, how do we define it? So phi of G, if G is an SL2C, phi of G is in some Lorentz proper group, and it acts on some vector in the Minkowski space, and it's defined to be the inverse image of G fx G Hermitian conjugate like that. We've seen that many times, so I won't elaborate on that. Okay, this is the group homomorphism that we are talking about. As it turns out, the group homomorphism is from SL2C to L. We write it in general as L4, but we are soon going to discover that that this is not an onto map because the phi only maps SL2C to just this thing in here. Okay, and so we might as well write this as to L sub 0, and that's it. This map never takes anything in SL2C to things in there. Okay? Okay, now, this is a homomorphism, but it's not a 1-to-1 map. It's in fact 2-to-1. In other words, G in there and minus G in there gets taken to the same thing. Okay, this includes the case E. E and minus E in here gets taken to this E over there. Okay, but any G in SL2C, and minus G is simply defined as that matrix whose elements are all with the opposite signs of the original one. That's minus G. Okay, and so G and minus G, both of which gets taken to the same thing in here. Now we have also found that there's a restricted homomorphism. Restricted to the subgroup SU2 inside of SL2C. And so here's a picture. Here's SL2C. Here's a subgroup, which is SU2. This is a group of special unitary 2-by-2 matrices. Okay? And you can easily prove that it's a subgroup because the identity 2-by-2 identity is in this guy also. So it's the identity as well as of the whole thing. This is L0. And we see that the restriction of phi to SU2 maps to where? Maps to SO3. proper rotations in Minkowski space, rotating only the spatial vectors in there, okay? And so we then kind of represent the whole thing. You can either remember it in terms of this picture, or you can, I think that's what we did in the text. We wrote down a couple of lines like this, that phi maps from SL2C to SO13, which is L sub 0, which, of course, is a subgroup of O13. Okay, there's difference between SO13 and O13. In here, the determinant must be equal to +1. This kind of determinant plus or minus 1. Okay, group of that's a whole Lorentz group, by the way. Sometimes we write it like that also. This is L4. Okay, and this map is 2 to 1 on 2. 2 to 1 on 2. So everything in here has a pre-image in here. That's what's meant by on 2. Okay. Now, SU2 is a subgroup of SL2C. And so there's a restricted homomorphism, phi restricted to SU2. And this maps 2 to 1 on 2. To what? To SO3, which is a subgroup of O3. And of course, SO3 is a subgroup of SO13 also. So you could write a relationship like that. And O3 is a subgroup of O13. So this kind of represents the entire story, okay, of the relationships between these. All of these are groups, okay? This is a group, 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 this is a group. The relationships between all those groups, here, like so, okay? And pictorially, you kind of get to this picture in here. It's almost in those statements in here, we disregard these three, because none of these things in here have a preimage over there, because the entire homomorphism only maps to this subgroup. This is the proper orthogonal subgroup. Okay, now. Related to that, I guess in the course of proving all these statements that we have just made in here, we've required a couple of very important facts, which can be proven, and the proofs are shown in the text, but I don't think I want to go into that in any sort of detail in here. The first one is a generalization of Euler's theorem in three-dimensional rotations. This concerns some general element in here. Supposing there's some, remember what Euler's theorem states, that any general rotation of three-dimensional space can be written as a product of three rotations, two of which around the third axis and one around the second axis, and so on and so forth. And so similarly, any general element in the proper orthogonal Lorentz group, call it lambda, can be written as a product of three things, two of which are simply rotations in three-dimensional space. R and R prime are rotations in three-dimensional space, and R3 is a Lorentz boost along the third spatial direction. Okay, so that's the interesting generalization of Euler's theorem. So generalize Euler's theorem in Minkowski space. Sort of. Okay. I don't think it's called generalized Euler's theorem, but I suppose it's kind of useful as a mnemonic to remember roughly what it states. Okay, and it's interesting. So you can have a Lorentz boost, for example, in an arbitrary direction. But the interesting thing is you can always write it in terms of a boost along the third dimension and a couple of rotations flanking it. Okay. So as long as we know how to find the preimages of these three things, which we do, okay, then we can just entirely work with this group SL2C. okay, which is in some sense a kind of a simpler thing in some senses, because these are dealing with 2 by 2 matrices in here, okay. The only thing is that you have, whenever you make a transformation, you have to do the transformation like this. These are transformations of remember what fx is. If x is some Minkowski vector, fx is a 2 by 2 Hermitian matrix, okay. And so then, if you want to do a Lorentz transformation on the vector x, then you first transform it to a 2 by 2 Hermitian matrix, and then you flank it left and right by G and G dagger. That itself becomes a 2 by 2 Hermitian matrix also, and then you take the inverse map, bring it back to the transformed Minkowski vector, which would be this thing. Okay? Okay. Now, we know that Euler's theorem says that any rotation can be written as R3, R2, R3, different angles, theta, psi, phi, something like that, right? So as long as we know the preimages of R2 and R3 and the preimage of B3, which we all know, which we have worked that out before, then we can work out the preimage of that thing in SL2C, which corresponds to a particular proper orthogonal transformation. The preimage of now let me just might as well write that out explicitly. The preimage of a rotation about the second axis is in fact plus or minus, because it's double, plus or minus business over there. Exponential of minus I theta over 2, sigma 2. But sigma 2 is the second Pauli matrix, or sigma y, which is a 2 by 2 Hermitian matrix. Okay. This whole thing is definitely in SU2. Okay. Because sigma 2 is Hermitian and there's an I in here, so this thing makes this a unitary operator, and you can write this in terms of a unitary 2 by 2 matrix with determinant plus 1. Okay. Similarly, now we have R2, so we just need another one for R3, and it's the same thing. We can write this as plus or minus exponential minus I theta. Let me use a different angle in here. Rotation by psi, angle psi about the third axis. So this is psi over 2 sigma 3, like that. Okay? Well, in principle, that's all we need. But actually, it's not too hard to see from this, and this is one of the exercises. I'm asking you to prove that the preimage of a rotation about any direction in three-dimensional space. So let's say you've got three-dimensional space, and this is some direction which is characterized by a unit vector n in here. And the rotation, let's say rotation about the axis n by an angle theta. You can kind of guess from these two what that preimage ought to be. Otherwise, in other words, what SU2 matrix would get taken by this homomorphism to this particular rotation, and the answer is plus or minus exponential of minus I theta over 2 n vector dotted with sigma. And this notation simply means that the x component of this unit vector times sigma x, or sigma 1, plus the y component of this times sigma 2, which is sigma y, plus the z component times sigma z. So since all of sigma x, y, z are 2 by 2 matrices, this thing is also a 2 by 2 matrix. Obviously, it's a unitary operator also, and it turns out to be some matrix in SU2. Okay? And clearly, you see that in the cases of rotations about 2 and 3, it just sort of reduces to these. We've worked these out explicitly. This one needs to be proven. The proof is not that hard. I've given you the solutions already, actually. Okay, it's interesting to see how that goes. But this is a general formula. This sort of thing is very important in quantum mechanics. Why? Because in quantum mechanics, it's only in quantum mechanics where you have to deal with spin systems. Classically, you don't have spin systems. Spin systems are described by two-dimensional vectors. Right? So when you want to rotate a two-dimensional spin vector, some quantum mechanical state, you use this kind of operation. So the sigmas, in other words, are two-dimensional representations of the Lie group of SO3. Two-dimensional representations of SO3, okay? And you can have various other representations, also two-dimensional representations, three-dimensional representations, four-dimensional representations, any integer value representations of SO3. This is a two-dimensional one, which again is of particular importance in quantum mechanics because these are the things which apply to dealing with quantum spin systems. Not just spin systems, but any quantum two-dimensional systems, okay, which get transformed by three-dimensional rotations in this particular one. Okay. Now, also, there's this fact that, which is actually quite easy to understand, that if you take at, there's a theorem which goes like this. If you look at vectors in Minkowski space, and see, I represent it like this. This line in here represents three spatial axes, and this is a time axis. And so you draw what's called a light cone. Okay. Sort of represented by this sort of a picture in here. Along this line in here, any vector, you know, on the surface of this light cone, so to speak, has length equal to exactly 0. Any vector in here, if you use the metric, I think the metric we're using in this chapter is -1, 1, 1, 1. Okay. So the length of a vector in here is x squared, is defined to be minus t squared. Actually, there's a c in here, but c is equal to 1 in natural units, plus x squared plus y squared plus z squared. Okay? So depending on the values of those four coordinates, the square of the vector x can either be positive, 0, or negative. Okay? If it's negative, that means this t component is bigger than the sum of these three. Okay? Then we speak of some vector being in here. Okay? That's the so-called time-like vector. A vector in here is the so-called time-like vector. Okay? Time-like. This is time-like. Both in here, this is called a forward light cone from a certain origin because this is where t is positive. And this other, the bottom half of the light cone is called a backward light cone because that corresponds to values of negative t. So if you go to some vector over here, it's clearly the case that x squared plus y squared plus z squared is bigger than t squared. So here, this is when x squared is less than 0. Over here on the light cone, this is when x squared is equal to 0. Here is when x squared is bigger than 0. So if vectors in here are referred to as being vectors in are referred to as time-like vectors, vectors lying on the surface of the cone are referred to as light-like because they somehow travel at the speed of light if a particle going from one point on the surface of the cone to another. And then vectors out here are called space-like vectors. Okay. These can be reversed if you change the signs of the metric in here, but that's kind of immaterial. The important thing is that you can divide all of Minkowski space into these different regions in here. Okay. Now, I guess we choose this convention. You don't have to, but if you choose this convention, then obviously physical particles can only, let's say if you start off an event over here, and there's some event that goes like this, since a physical particle having mass, at least those having mass, can only travel with speeds less than the speed of light, okay? then they, physical particle, what's called a world line of a physical particle with mass can only lie within the light cone. In other words, in the time-like region in here. Okay. It cannot go from here to here, physical particle with mass, because that would be when it would be like traveling with a speed that's bigger than the speed of light. Okay. Light, of course, have to travel along the light cone, along the face of the light cone. Okay, that's when c is equal to 1. Okay. Obviously, when something travels with the speed of c, x squared plus y squared plus z squared is equal to t squared. Okay, so that's when it's on the light cone. So separation between these three regions, space-like, time-like, and light-like. And there's a theorem which actually is not too hard to prove, that any element, any Lorentz transformation within this proper orthogonal group, in other words, any Lorentz transformation which is connectable to the identity by a continuous line, every point of which lies inside of this subgroup in here. Okay. Those kinds of transformations in a proper Lorentz group, proper orthogonal Lorentz group, has to preserve the particular light cones, let's say. Okay. So something in here is always taken to something in the same light cone. So if something is already in the forward light cone, it always gets taken to another place in the forward light cone. If something is in the past light cone, it always gets taken to some things in the past light cone. It can never either go from here to here, that's very clear, or it can never go from here to here. Why? Because the fact that it can never go from here to here is quite obvious, because if you go from here to here, then you will have changed the length of the vector, which is not allowed by any Lorentz transformation, right? But there's also a part that says that, the time sense is preserved, so to speak. Things inside the forward light cone, the light cones, the half light cones are always preserved. That's a theorem which can be proved, which I won't go into any details. Okay. So finally, the picture is this, that this is a connected space, although as we'll see, it's not simply connected. This is also a connected space, because any 2 points can be joined by a path, so to speak, all of whose points lie inside of this. But the difference between this and that is there's an important topological difference, is that this is simply connected. This is simply connected. This guy is doubly connected. Now, what is meant by these terms? Simply connected means that if you draw any loop inside here, that loop can always be contracted to a point. Okay? But if you draw a loop in here, that loop may not be contractible to a point. But if you find a way to loop around twice, then that double loop can be contracted to a point. In that sense, it's doubly connected. It's a very different topological property. One is simply connected, that other one is doubly connected. So the last thing I want to do is to show you how this can be achieved, and I choose to illustrate that in terms of the subgroups, just the rotation groups themselves, with respect to the simply connectedness of SU2 and then the doubly connectedness of SO3. SO3 is connected but not simply connected, it's doubly connected. SU2 is simply connected. Okay? Now, to do this, let me then start off with a description of the topological properties of SU2. I think, David, was you asked last time, what is the topology of SU2? Okay? I think I told you it's S3 embedded in 4-dimensional Euclidean space. That's what it is. Now, that's quite simple to see. just leave this picture in here. And the 4 globs in here means those 4 globs are not connected. There's no way to get continuously from something in one glob to something in another glob. Okay? Disconnected. L4 as a whole is disconnected. L0 is doubly connected. I don't know about these others. Probably doubly connected also. Okay. Okay, now let's look at SU2, which is a subgroup of S of L0. Now SU2 is a 2 by 2 unitary matrix. So I'm going to make the claim that any SU2 element can be written like this in terms of 2 complex numbers. Where A and B are complex numbers. Like that. Okay? I think it can be quite simply seen that what is a unitary matrix? A unitary matrix is one whose inverse is equal to its Hermitian conjugate. Right? Now what is the Hermitian conjugate of this? Remember, Hermitian conjugate is, first of all, forming the transpose of the original matrix and then taking the complex conjugates of all the elements. Okay? So then we have what? We do this at the same step, right? So we have A. Oh, by the way, bar means complex conjugated. Okay? At least in this notes. Usually in your complex analysis books, you use the star to represent the complex conjugate. But in geometry, star means something else. Okay? So let's do the bar. But it doesn't really matter as long as you know what we're talking about. So what would this one be? Oh. Negative b. Remember, you take the complex conjugate. Complex conjugate of b bar is b. Okay? This is negative b. So what's this one now? B bar. And this one would be a. Okay? And believe it or not, if you multiply this by this, let's see what we get. A bar minus b, b bar, a, multiplied by a b minus b bar, a bar. So the first one is what? Absolute a squared, right? A times a bar is a squared. Minus minus is a plus, plus b squared. And this one is what? A bar b minus a bar b, right? So it's 0. Similarly, this one is also 0. AB bar minus AB bar. And this last one is b absolute square plus a absolute square. Now, why do I claim that this is the identity matrix? It is because of the S requirement, that the determinant of this guy must be equal to 1. What is the determinant of this guy? It is a absolute square plus b absolute square. So the general G in SU2 can be written in this form, provided absolute a square. This is a constraint relationship, which is very important. Provided that these two complex numbers satisfy this condition, then that's a general element in SU2. Okay? So an SU2 element is just characterized by 2 complex numbers. Okay? 2 complex numbers are 4 real numbers. And so let's write it like this. Let's write A as x1 minus I x2. We introduce 4 real numbers, x1, x2, x3, x4, right? Write A as x1 minus I x2, B as x3 minus I x4, like that, okay? So then, A absolute squared plus B absolute squared must be equal to what? Must be equal to x1 squared plus x2 squared plus x3 squared plus x4 squared. And that, as we saw, is required to be equal to 1. Okay? So you take 4-dimensional Euclidean space, right? Let me draw it like that. x1, direction, x2 direction, x3 direction, x4 direction. Any one point in here is just any quadruplet of real numbers. But if you subject the 4 real numbers to this requirement, then you have what is called S3 that is embedded in S4, pretty much like in 3-dimensional space, the spherical surface is subjected to what condition? x1 squared plus x2 squared. Spherical unit surface plus x3 squared is equal to 1. You just add one dimension in there. This is called S3. Okay? The 4 coordinates of S3, considered as coordinates in 4-dimensional Euclidean space, must satisfy this condition in here. So that says topologically SU2 is like S3. It's like a real. SU2 is like a real space. Okay? Which is a 3-dimensional space. Now this space is, don't quite know how to visualize it, but you can certainly project it to 3-dimensional space or even 2-dimensional space. Okay? For example, you can take 2 of the elements to be equal to 0, and then you get yourself a circle on a plane. Yeah?
Since there are 4 coordinates, would it be a 4 sphere?
No, this thing is 3-dimensional because you have 4 coordinates subjected to one condition that cuts down the number of independent variables to 3. So it's a 3-dimensional manifold. S3 is called, and in fact, you can define general Sn in this manner, right? You introduce 5 coordinates and introduce this requirement. The sum of the squares of all of them is equal to some particular thing. Then you cut down on the number of dimensions by 1. Okay? So S3 can be thought of as a 3-dimensional sphere embedded in 4-dimensional Euclidean space. Euclidean because they're all plus signs in here, right? Whereas if you use the Minkowski, one of these would have an opposite sign to define the length, right? So it's Euclidean space. So all these different things are connected to each other in sometimes kind of unobvious ways, okay? So SU2, you look at it as like a complex thing in here, and then all of a sudden you can think of it as some sort of real spaces, and so on and so forth, okay? So SU2, topologically, we call this homeomorphic. I think that's a term, right? Those of you who are taking mathematics courses, topologically equivalent is called homeomorphic to S3. Okay. Now, let us use a mapping to map something in SU2 to something in fact, 4-dimensional Euclidean space. Let's call that mapping H. G is equal to this matrix, G in SU2. In general, this matrix AB minus B bar, A bar. Use this mapping, which we call H now, to map onto 4-dimensional Euclidean space. And we just define x1, x2, x3, x4 according to these equations in here. Okay, so this gives us a mapping from something in SU2 to something in 4-dimensional Euclidean space, which of course would have to lie on a 3-dimensional sphere.
What if we change the sign to a minus sign?
Where? Oh, so that all turns out to be plus. Yeah, actually, does it matter? I think it does. Okay. In any case, you define the 4 real variables in this way. Okay. There's something I forgot to mention. Oh, I think in the mathematics or sometimes in the physics literature, these 2 numbers have a name to it. They're called a Cayley-Klein parameters. I don't know if you've heard of this term in there. These numbers A and B are called name after these 2 mathematicians, Cayley-Klein parameters. I think Cayley was a British mathematician who made contributions to group theory, and Klein, of course, was a famous German geometer, did many things in geometry. Especially famous for setting up the so-called Erlangen program, says that geometry is the study of certain kinds of isomorphisms and so on and so forth. 19th century important German mathematician. Okay, now there's an important theorem in topology which I'm not able to prove here, and that is, I think I wrote this as an upper 3 in the text, but it doesn't matter. Important fact. Sn for n bigger than or equal to 2 is always simply connected. It's always simply connected. Obviously not true for S1 because S1 is just this loop in here. And now if you take a loop in here, which means the whole thing, you can't contract it to a point, okay? You cannot contract it to a point. If you take a loop on S2, S2 is the two-dimensional surface, right? You can actually see, you take any loop in here, always shrink it down to a point. During the process of shrinking, all the intermediate loops have to still lie on that surface, okay? You can always imagine shrinking it to a point. But you can't do it for S1. The important mathematical theorem that is that you can simply shrink any loop in Sn for n bigger than or equal to 2, shrink it down to a point. All the intermediate loops have to remain in the surface. Yeah.
Is that the Poincare conjecture?
It is not the Poincare conjecture. I don't think so. No. The Poincare conjecture has something to do with, especially, does it have to do with S3? It has to do with S3, but it's not this fact.
It's all smooth, simply connected. 3 manifolds are homomorphic
To S3?
To the sphere.
To the sphere.
Yeah.
But I don't think it's this one. Okay. This one simply refers to S3 itself and Sn. Okay. Yeah, the Poincare conjecture, of course, is an enormously complicated thing. It's only been recently proved, as you know. Okay. Okay. Now what can we do with these things? The idea is that obviously SU2 is homeomorphic to S3. S3, of course, is simply connected. You know that, so that means SU2 is simply connected. Okay. That means you take any loop inside, you can always shrink it to a point inside of SU2. But if you try to take any loop in SO3, as I mentioned, sometimes you cannot shrink some loops down to a point. But you can show that if you wrap around twice of some loop that's not shrinkable, a single pass loop that's not shrinkable down to a point, but if you wrap it around twice, you then can shrink it down to a point. It sounds kind of strange, but actually that's the way it is. That's what makes it doubly connected. So let us finally kind of show how this works out. But before that, let me introduce one terminology first. That, the relationship between SU2 and SO3, and similarly the relationship between SL2C and L sub 0, is that we say that this one is a universal covering group of the other one. Okay? Universal covering group. SU2 is a universal covering group of SO3, and SL2C is a universal covering group of L sub 0. Now, what is meant by universal covering of one group over another one? Has a sort of the definition is simple. So let's say if one group that we call GUC, UC for universal covering group, is a universal covering of another group if there exists a continuous homomorphism rho which is only locally one-to-one, but may not be globally one-to-one, okay? So this has to be locally one-to-one. But not necessarily globally one-to-one. And meanwhile, this thing has to be simply connected. It's a simple connectedness which qualifies as this which qualifies this first group being called a universal covering group. Okay. In other words, if we take a look at, just take this example in here, SU2 covering. This guy covers this, okay? Covers SO3. That means everything in here, and there's some, in fact, the group homomorphism in our case is phi, but let me just use this general symbol phi in here, this group homomorphism. Everything in here has a preimage over here, right? So it covers this guy in here. And also, this guy is simply connected, but this guy need not be simply connected. And it's locally one-to-one, which means that if I take some element in here, there's a local region where there's a one-to-one map between this local region and some local region in here, locally one-to-one. But not globally, because let's say there's a G in here, which is in that region, which gets mapped to whatever rotation that is in here. There's something which may be very far away, minus G, okay, which gets mapped to the same thing in here. So it's locally one-to-one. That means within a certain neighborhood, there exists some neighborhood where the mapping is one-to-one, but that mapping is not globally one-to-one, okay? So if the mapping is locally one-to-one, and this is a homomorphism, and the first one is simply connected, then this thing is called a universal cover of the other thing. It's usually much simpler to deal with the covering group. Why? Because it's simply connected. That's that topological property. And this is a very useful fact. That's why, why do we deal with, in physics text, we don't usually deal with SL2C matrices, right? But in mathematics, we deal with the SL2C matrices because that is a connected space, okay? And we can prove sort of interesting topological theorems about it and so on and so forth, such as the fact that this thing is homeomorphic to the spheres and so on and so forth, okay? Now finally, let me show you why using this map in here, why SO3 is doubly connected even as SU2 is simply connected. And also, as I said, it's simpler to use this because these are 2x2 matrices, whereas things in here are, in the Lorentz case, are 4x4 matrices, like that. Okay. Although, price you have to pay is, I erased that already, that you have to stick the G and the G dagger one on both sides. Okay. So what? Okay. Now let us look at the SU2. And use this map to map it on some point in four-dimensional space. And simply connected, there's a technical jargon to express this fact. We say that the homotopy group just has the identity element. The homotopy group has to do with the kinds of loops that one can form in a certain space. That's a topological. That's an algebraic. That belongs to the realm of algebraic topology. Okay, you study the topology of manifolds using the algebraic method of groups. In this case, you introduce what's called a homotopy group. I won't go into details. And mathematicians can calculate those homotopy groups for certain important spaces. Sometimes they're very hard to calculate. Sometimes they're easy to calculate. But as soon as you determine that the homotopy group just is a trivial group which consists of the identity alone, then that's equivalent to the sort of the intuitive picture that any loop can be shrunk down to a point, okay? If the homotopy group is anything more complicated than that, then it's not simply connected, okay? It's called a first homotopy group because it's a loop. A loop is a one-dimensional subspace. There are higher order homotopy groups, H2, H3, H4, and so on and so forth. Those are refer to two-dimensional subspaces. Loops are things without boundaries. So you can, in general, think about two-dimensional subspaces which don't have boundaries and three-dimensional subspaces which don't have boundaries and so on and so forth. I won't go into the details in here. That's algebraic topological methods, okay? In physics, we don't care about those things that much. except to realize that it's there and sometimes to make use of the results. So let's look at this SU2. And supposing we look at this map. Let's say we pick some SU2 which corresponds to a rotation. I erased that. Suppose I pick this particular G in SU2, which, okay, we pick the plus sign, let's say, so that this has determinant plus 1 minus I over 2, 0, 0, e to the I theta over 2 like that. Okay, and we saw that this is this gets mapped by the group homomorphism to rotation about the second axis by an angle theta. Okay, if rotation is by an angle theta, then the angle which enters in here in the SU2 is theta over 2. This factor of 2 is a reflection of the 2 to 1 nature, okay, in a manner of speaking, between SU2 and SO3. So the same rotation can be represented by these two different matrices. We want to take this one, okay? We want to take this one in here like that, okay? Actually, if you use minus sign, the determinant is plus 1 also. But we want to take this one because we want that to be the one that's connectable to the identity directly, okay? But it doesn't really matter. In any case, we take this G and let's use this map to get us to some point in 4-dimensional space. Now, remembering that this one is what? This first one is called A, right? This first one is called A. So B is equal to 0. A is e to the minus I theta over 2. B is equal to 0. So what is x1 and x2 in this case? x1 must be what? If the whole thing is e to the minus I theta over 2, x1, the real part, must be cosine theta over 2. And the complex part must be minus sine theta over 2. In other words, x2 is sine theta over 2. Okay? Maybe that's the reason why we choose the minus in there. We want it to be plus cosine theta over 2, one of the reasons, and sine theta over 2. And what would these two be? Since b is equal to 0, that would be 0, 0. Okay? So this gets kind of projected to where? To the 4-dimensional space where the third and fourth coordinates are equal to 0. In other words, to a 2-dimensional projection of 4-dimensional space. In other words, a plane. Okay? So it gets projected to a point on the plane. We forget about the third and fourth dimensions, so the coordinates are always 0. This is x1, this is x2. And now you see what? How do you make the mapping in here? You know, when theta is equal to a certain quantity between 0 and 2 pi, theta over 2 is between 0 and pi. All right. So if I start off with theta is equal to 0, which is the identity, okay? This is the identity in here, so to speak. Okay. Theta is equal to 0. That means 1, 0. Okay. 1, 0 is this point. This length is 1, like that. Okay. Start off with theta is equal to 0. As theta increases, what happens to this point? This point just moves around in a circle, right? When theta gets to pi, it travels to pi over 2, right? When theta gets to 2 pi, then over here, it has just made a half circle, a semicircle, right? Okay? In other words, if this is e in here, this is minus e in here. So now the rotation is a closed loop in the rotation SO3 group is when theta goes from 0 to 2 pi. That certainly forms a closed loop in the rotation group. One round, once around. Okay? But on the projected space of this three-dimensional sphere projected further onto the two-dimensional, well, actually this is projected onto the one sphere. Okay, it's just around a circle in here. This is definitely not a closed loop. It's only gone kind of half a loop. Okay, once around in the space of rotations has only gone halfway around in the space of SU2, so to speak. Okay. Now you can. Now let me take you to the picture, back to the picture of actual rotations. Now you remember that in the rotation picture, the manifold of the rotation group is pictured as a solid ball, okay, whose length, whose radius is pi, with antipodal points equated, okay, identified, so to speak. So let's say this thing represents a rotation. Oh, by the way, sorry, this thing represents a rotation about R3. So let me draw this solid ball in here. And let me make this identical. This represents something in this, so consequently this represents something in SU2. Now I'm going to do the homomorphism, so this brings me to something in SO3, but something in SO3 can be represented as a point inside or on this sphere in here. And where's the identity? The identity is represented where? Right there at the center. No rotations, okay? When theta is equal to 0, okay? Here theta is equal to pi. This length is pi, so now why is it not 2 pi? Again, of that fact, a rotation about a certain axis by an angle that's bigger than pi is equal to a rotation about 2 pi minus that angle about the opposite direction. We have proved that fact also. So that's why we only needed to go from 0 to pi, okay? When you take into account all the possible directions. So let's say you start off with the identity. That means you start off with here, right? That's the identity element, okay? Some element in here would be a rotation about the third axis by an angle equal to this much, about this axis, okay? So now what is this point then? A rotation about the third axis by what angle? Pi, right? Because the radius is pi, like so, okay? So now, let's take it here. If I go, let me use color chalk so that we have, let's say we take this path, okay? When theta goes from 0 to pi, that is from here to here, okay? Theta over 2 has gone from 0 to pi over 2. So it's going here, okay? So let me represent this. Make a correspondence like this in here, okay? So if I've gone around this path in SU2, I've gone this much in SO3, all right? And now, let's continue, right? Suppose we continue by going over here. When theta goes from pi to 2 pi, okay, like so, then you'll see that this can be represented by, let me see. Okay, I'm going to represent it like this. But this point's the same as that point, right? So I go here, boom, I'm here already. And the yellow path is then represented by this one, going back to this in here, okay? This is E, this is minus E in here. Minus E and E both gets mapped to E. Yeah?
Those lines are inside the sphere, they're not.
Yeah, they're inside the sphere, right. This is a solid sphere. Solid, I use this kind of pictorial device. Solid sphere, okay? Now I keep going. If I keep going, like this one in here, that would be like this one. Okay? And finally, let me complete it by going like this. Now, if I've gone to here, boom, I'm down here again. So I'm back up to here, okay? Like so. You see? This is the kind of correspondence that we are talking about. So a single loop in SU2 is then a double loop, because we've gone around this loop twice. Once like this, and another time like this. It's like a double loop in SO3. A single loop in SU2 is like a double loop in SO3. Okay? We have already seen that a single loop in SO3, meaning this and then this, cannot be contracted to a point because it corresponds to an open curve in SU2. All these topological properties, have to correlate like this. But a single loop in SU2 should be, which corresponds to this double loop in here. And our business now is to understand why in this picture, one single loop does not contract to a point, but a double loop will. Okay? So if you remove two of the lines in here, let's say if you remove the purple and the blue line in here, it's not possible to contract the orange and the yellow together to a point in the three-dimensional sphere. That is topologically SO3. So there's a kind of a pictorial way to show you why a double loop is deformable to a single point. This represented by this sequence of pictures. In the text, let me just finally draw this to show you how this feat can be achieved. So we take it through several stages. We take the contraction, so to speak, through several stages. So first, we start off with a double loop. Oh, I have to gather together my color chalks in here. Purple, blue, yellow, the orange, like that. So I start off with a double loop picture first, right? There's a center. I have what? Orange, yellow. Darn, it's hard. Orange, yellow, and then purple, blue, purple up, purple, blue. This is a double loop. Purple, blue. Okay, this is the double loop. Okay? Double loop. Okay, I start the first contraction like this. I take one of the lines. This is the center. I take one of the lines and move it across like this. So let me take the orange, yellow, okay? And move it like so. Orange. This is some kind of a deformation, if you will, okay? Continuous. I can do it continuously like this, right? And take one of the lines in here and move it like this. Let's say the other two remains the same. So I have this, and then I have this. First stage of deformation, okay? Let me call this point, let me label the different points. Put my white chalk in here. This point P, you see, but this is also the same point, so I call it P also, okay? Antipodal points, right? Similarly, this is Q, I call this Q, okay? So the first thing, you take one of the lines and do it like this. It's definitely a continuous deformation. So what does your double loop look like now? Double loop looks like this. Bump, bump, and then bump, bump, like that, okay? And next step, continuous, okay? So let's say this is a point Q, this is a point Q in here, and originally there was a line like this, and this is a point P, this point P here, P here, P here. Now, let me, now, originally these two lines cross at this center point, which is the identity, but certainly you can pull it away from the identity by continuous deformation, okay? So you can imagine doing something like this. So take this one, for example. When it comes to here, you pull it away from the identity a little bit, okay? And, well, you don't really have to, but let me continue that with the yellow chalk, like so. So it still goes like this. You do a similar thing with the other one. And so you pull it away from the identity. Okay, like so. Still a double loop. Okay, so double loop because you can imagine starting from any point in the loop, such as here, for example. You go boom, all of a sudden you're here, boom, and then you go here, boom, and all of a sudden you're here, and then you go back to the original point. That's a continuous deformation from this loop down to here, okay? And the next step is now you can imagine pulling these guys together, continuous deformation also. So P becomes a new point P prime, and Q becomes a new point Q prime. And so now I don't need to differentiate between the different colors, so let me just draw it as one continuous. You take this one in here on the left, and you pull it apart. Meanwhile, continue to deform. Just take this whole thing and kind of move it over like this, okay? Similarly, this other can be like that. And now these are different points now, so I'm going to call this P prime, Q prime. But this one and this one are still, you see, antipodal. These two are still antipodal, okay? So this is P prime and this is Q prime. It has to be antipodal relationships like that. All right, is that okay? Now finally, it is very obvious what to do. You continue to pull them closer together so that, let me draw one more picture in here. This is a final, next to final picture. So, and then pull them closer together like that. Okay? Such that this point corresponds to this point and this point corresponds to this point. And then the final step is what? A point, antipodal point. Points, antipodal points, which are the same point. Okay? Just a point. Antipodal points. Which is a point, so therefore we have managed to continuously shrink a double pass loop to a point, whereas you can't do that for a single pass loop. Okay? So that demonstrates so-called double connectedness of the SO3 group, which has profound consequences in the theory of, because it has to do with rotations in the quantum mechanical theory of rotations in quantum mechanics and so on and so forth. Okay? All this business about a double representation and so on. So with that, I end this chapter. Now this is a whole bunch of the story, namely the representation theory of the Lorentz group, which I haven't had time to introduced yet. That in itself is a very long and detailed subject. If you were to do it, you would do it roughly along the same lines as how we developed the Jij representations of those operators, the infinitesimal generators, okay, of the SO4 business and SON business. You would do something similar, but because of the different topological character and so on and so forth, the story is much more complicated. But finally, once you introduce all those different operators, then there's a way to correlate those with the kinds of particles that are possible in space, such particles of integer spin, particles of half integer spin, in other words, bosons and fermions, and so on and so forth. Okay, so the representation theory of the Lorentz group is basically underlies the whole story about what kinds of physical particles there are in our universe as we know it today. Okay. Of course, nowadays you hear of such things as supersymmetry and so on and so forth. That is a symmetry which kind of unites bosons to fermions, bosons on the one hand to fermions on the other, which of course is not included within the representations of the Lorentz group. But the Lorentz group is important enough. Okay, it's a basis of high energy physics, basis of quantum field theory, so of quantum field theory of high energy physics, and so on and so forth. Let's take a little break, okay, before we go to geometry, talk about gauge field theories and so on. So we're going to go into the second main part of the course, which is applications of basic differential geometry to physics. And the geometry that we are talking about is in mathematical terms called a theory of fiber bundles, mostly vector bundles, and maybe to some extent what I call principal bundles also. On the physics side, it's called a gauge field theory, which is the basic physical theory that is used to describe all of the fundamental forces that we know now, okay, including gravitation, okay. There's a certain kind of gauge field theory also. So I want to kind of bring this in gradually, first through familiar physics examples. The physics example I've chosen to use is quantum mechanical, but for those of you who haven't taken the quantum mechanics courses yet, don't worry about it too much. We're going to try to smoothly step in. For those of you who have taken my classical mechanics class, we've already talked about that to some extent through the idea of the covariant derivative of vector fields on a certain manifold. So these ideas, the connection, one form, the covariant derivative, parallel translations of vectors are all part and parcel of the same core group of mathematical ideas that forms the theory of gauge fields in physics. I think otherwise also known as the theory of moving frames in geometry. Okay, we'll explain why the origin of that terminology a little bit later. So let's step back and look at the quantum mechanical description of the interaction of a charged particle like an electron with the electromagnetic field. Okay, there's a very well-developed theory for that called the theory of quantum electrodynamics, where everything is treated quantum mechanically, including the electron and a photon and so on. Everything is quantized, okay? But that's quite complicated. And, it involves the use of, doing all those Feynman diagrams and things like the calculations of all of those and so on and so forth. Usually, when one is introduced to these kinds of theories, one looks at the what is called a semi-classical description of quantum electrodynamics, where you treat the material particles such as the electron quantum mechanically, but look at the radiation field as a classical field. That's why it's called semi-classical treatment. There's still a lot of good results, and that is the kind of quantum electrodynamics that's basically used in the description of low energy interactions such as absorption and emission of radiation by electrons in an atom or molecule and so on and so forth, okay? And similarly, condensed matter systems interacting with the electromagnetic field are quite often described by this semi-classical fashion also. So the beginning point is this. Supposing, let's say, we think about an electron, let's say the hydrogen atom, a single electron in a hydrogen atom. it interacts with the radiation field, okay? Now the electron already is subjected to some kind of radiation, not radiation in this case, but a static Coulomb field, which comes from the Coulomb force between the nucleus and the electron. But let's imagine that you shine a laser light on the atom, okay? So it interacts with some external radiation field also, okay? That laser light, of course, may just bounce the electron off somewhere, or it may cause the electron to jump to a higher excited energy state, or it may simply be scattered by the electron. All kinds of things can happen. We want to find a basic way to describe this basic form of interaction. Now, you know that in quantum mechanics, non-relativistic quantum mechanics, we write this thing called a Schrödinger equation, P squared over 2m plus potential energy of the electron. Psi is the wave function of the electron. Write this in terms of the time-dependent Schrödinger equation. This is called the time-dependent Schrödinger equation, okay? I think all of you probably have seen this in one way or another, okay? If you have taken 235, you know this equation. Now in the case of the hydrogen atom itself, this so-called electrostatic potential, we just write it differently using a different symbol. This is a spherically symmetric potential like that, E phi, okay? That's the simplest description of the quantum mechanical Kepler problem, which we did using group theoretic means a few chapters back, using the group SO4. But you know, in other quantum mechanics courses, of course, you will have learned how to solve actually this differential equation, which will then come out to depend on the spherical harmonics and the Laguerre polynomials, much more complicated story, and so on and so forth. We don't want to solve this equation. We simply ask the question: if, in addition to this potential, there's a radiation field that's impinging on the electron, then how do you describe that radiation field? Okay. For this, it's actually not all that straightforward, not all that simple. One has to, first of all, describe the electromagnetic field by its vector potential. Okay. In other words, the vector potential A, such that del cross A is equal to the magnetic field, okay? And actually, relativistically, these three components of the vector field together with the scalar potential itself form the four components of what's called a four-dimensional vector potential. But let's just look at it like this first. How do we then, with the presence of this A in here, incorporate this A into the Schrödinger equation, so that that equation will describe the interaction between the electron and the radiation field? Okay, that's a problem. And as I said, it's not quite so straightforward. You have to go through what is called the Hamiltonian formulation of classical mechanics, which unfortunately we haven't quite gone to yet in our classical mechanics course. But let me just briefly mention the result. Is that in Hamiltonian mechanics, you identify certain so-called generalized coordinates, and then you then calculate something called canonically conjugate momenta, okay, one for each coordinate, and then write the Hamiltonian in terms of the canonical coordinates and the canonical momenta, usually denoted P and Q, P for momenta and Q for coordinates. They may not be physically momenta or coordinates in the sense that they don't have the usual units. For example, an angle, which doesn't have any length unit, may be used as a generalized coordinate, and then the canonical momenta would be the angular momentum, for example, which doesn't have the units of a linear momentum. Okay, but through the process of the identification of these canonical coordinates and the canonical momenta, then you can change the equation in this way. In this way, in here, this is regarded as the momentum that is canonically conjugate to this coordinate, okay? And the way that the radiation field is incorporated is this. Instead of P in here, you write P minus E over C times A, where I have explicitly written all the ingredients, E being the charge of the electron, and C is the speed of light, okay? In other words, in order to describe the interaction of a charged particle with a radiation field, you have to make this replacement in here. Everywhere you see a P, you replace it by this thing. Everywhere you see a P, you replace it by this thing, which, by the way, this was originally introduced, I think, by Dirac, and he called this the minimal coupling. I don't quite know exactly minimal in what sense. Maybe this is the simplest thing that one can do, okay? But it turns out to be the correct way to do things, okay? So if I have some radiation field, oh, by the way, then you know that classically, then you can find the electric field also, which is something like given the scalar potential and the vector potential A, then you can form both the E and B fields. And in principle, classically, knowing the E and B fields, then you know how to describe the interaction between a charged particle and the E and B fields, right? So this is the content of classical electrodynamics. But when you want to deal with it, the particle as not as a classical charged particle, but as a quantum mechanical particle, this is what you have to do. I cannot at this point show you exactly why. Later on, maybe in my classical mechanics course, I can demonstrate to you why this minimal coupling is the correct way to do Hamiltonian dynamics. And you see, there's a reason why this is called a Hamiltonian, right? Because it comes from Hamiltonian formulation of classical mechanics. Yeah?
So the momentum of variables, momentum observable, gets turned into the del operator. What operator does the A?
A is just considered as some function multiplied by the scalar wave function. You can look at it in the same sense as the position operator operating on psi is just a multiplication, okay? In that sense, yeah. So the Schrödinger equation then becomes like this, right? P replaced by P minus this thing, so P squared becomes this, 2m plus V R. The whole thing operating on psi is equal to I h bar d psi dt. Now here's the rub. In quantum mechanics, this is called turning classical mechanics into quantum mechanics. You replace P by h bar over I times the gradient operator in three-dimensional calculus, okay? And so then, immediately, I can write this Schrödinger equation in this way, minus h bar squared over 2m di minus I e h bar ai squared plus e phi. Oh, this is e phi in it. The charge times the potential is the potential energy, like so. Operating on psi is equal to I h bar d psi dt. Okay, look, there's an unfortunate circumstance in here. This I is not the same as this I, obviously. Right? This I is the imaginary unit. So for this reason, I guess as in the book, I'm going to change it to J, or in fact, I use mu, okay? But it's also unfortunate because mu here only goes from 1 to 3. Okay? We're here dealing with these three-dimensional vectors in here, like these guys in here, three-dimensional vectors. Okay? So everything is clear, right? So now, it's actually mu, that square means d mu d mu. D mu d mu. So it's like a scalar operator in here, okay? And these things gets raised and lowered by the Euclidean metric, so it doesn't really make any difference, okay, in this case, because we're dealing with three-dimensional vectors in here. And so this thing, of course, is a mu. But there are cross terms in here now, right, because of this square in here. In one of the terms, the derivative only acts on this. In the other term, the derivative acts on this guy also, because this guy also depends on positions. Okay? You see now, so that forms the sort of part of the complication in this picture in here. But I want to mention this fact that if one looks at this derivative in here, it is a covariant derivative. Yeah?
Are we doing this in natural units c equals 1?
No. I have written down, I'm missing a factor c. I better be careful. C. I think that's where it should go. Okay. Later on, you can go to units where h bar is equal to c is equal to e is equal to 1, but let's not do that for the time being. Let's just keep these things in there so that we have an idea of what kind of physics we are talking about. Okay. All right. So this thing in here, this operator, which we're going to write d mu defined to be ordinary partial derivative minus I e over h bar c a mu is in fact a covariant derivative, a covariant derivative. Okay, and I'll try to explain how this thing is in fact the same mathematical beast as the thing that we introduced in the classical mechanics course, just a little bit later on. Okay. In fact, I can sort of do that now. So, you know, if you have this coordinate covariant derivative of some function is then this operator acting on this function in here like that. Okay? So the covariant derivative involves an ordinary partial derivative and something else, plus some function of coordinates in here, because a mu being the vector potential in this case is some function of coordinates. The mathematical setting is something like this. Here's three-dimensional space, R3, and in this case, this is the base space of what we are doing our quantum mechanics on. And the so-called fiber is some one-dimensional complex space, okay? So one element in here can be represented by a wave function in here like that, okay, which is a complex valued function of real variables in this case, okay? Because the wave function is a complex valued function of real variables, okay? And we can consider that as a wave function is, so if this is a one-dimensional space in here, and then one point in here is some vector depending on the position in here. So this wave function is can be considered as no, sorry, a wave function is actually what is called a cross section. This is the complex line. This is a complex C1. Okay, C1. So this is the set of all complex numbers in here. Okay. So a vector field, if you think of this as a vector space, a one-dimensional complex space, if you think of what's called a cross section, like so, okay, which means at each particular position you choose a complex number. All right. At each particular position you choose a complex number. That's precisely what a wave function is, because it's a complex valued function of some real variables. Now, sometimes it can be explicitly a function of time also, but that only makes this R3 cross R, something like that. Let's not talk about a complication also, okay, in this case. Usually R3 cross some closed interval in R. Let me just consider this point first. So having this kind of geometrical picture in mind, the covariant derivative is then really the derivative of a vector field, right? Because this is a vector field. I choose a vector at each point in the space. So this is a vector field. All right? So the complex derivative is an operator which acts on a vector field, as we introduce it in classical mechanics, only that in classical mechanics we are talking about a tangent vector field. So here's this base space, and here at each point I introduce a tangent space. The tangent space is a vector space which has the same dimensions as the space of the underlying manifold. So if the underlying space is a two-dimensional space, then I have the two-dimensional vector space for a tangent space at that point. And obviously, I get a tangent space at every single point in the manifold. When they're bundled together in a certain way, it's referred to as a tangent bundle. Okay, this is called a line bundle. It's ordinary quantum mechanics because each fiber is just a line, one-dimensional, although it's a complex vector space. In the case of a tangent space of a real manifold, it is a real vector space in here. Okay. Now you recall that in classical mechanics, we introduce a frame, what is called a frame field, on the tangent space at each point. So we choose an orthonormal frame at each point. This is called a frame field. Okay. In the case of two dimensions, we choose it like this. It can be chosen in many arbitrary ways as long as it is a continuous change, okay, so to speak. The choose of a frame field is kind of like a cross-section on a principal bundle, okay? Now, we mentioned when you find the velocity, for example, velocity v is defined usually in lower division classical mechanics text is defined as some xi, ei being the position vector, okay? So the position vector, you differentiate with respect to time, you get the velocity in here. But here's the thing, if you choose a frame field where the ei's can change from point to point, instead of, in addition to differentiating the xi, you have to find a way to differentiate the ei's first. The differentiation of the ei is not a differentiation of a simple function because this is not a function in here, okay? So the idea is you can still use the product rule. So this is like x dxi dt. We write that as ordinary derivative. And then ei plus xi dei dt. But instead of an ordinary derivative, this has to be what's called a covariant derivative. That's how we introduce the covariant derivative. The covariant derivative is another structure that's imposed on the tangent bundle, if you will. Because in order to specify the covariant derivative, you have to write an expression for this. Some kind of small changes of these ei's as you go from point to point. That's why it's called a connection, okay? And in classical mechanics, remember we wrote something like this? How did we write it? We wrote this in terms of a matrix. In the case of two dimensions, then you would have something like dE1 is equal to omega 1, 1 E1 plus omega 1, 2 E2. In other words, I express the change in each basis vector as a linear combination of the two basis vectors in here. Okay? And it's a small change, so this has to be an infinitesimal quantity. Okay? So these things would have to be proportional to first order differentials. Differentials of what? Differentials of the coordinates, because it's in changing the coordinates, going from point to point, that you bring about those changes in here. Okay? In this sense, it's called a connection. Now, we saw in classical mechanics that if we use orthonormal frames, then this guy is an antisymmetric matrix, so the diagonal elements all go to 0. It's antisymmetric, so for the 2 by 2 case, there's really only one independent element, namely omega 1, 2. Okay? But in general, this is a matrix, right? It is omega 1, 1, omega 1, 2, omega 2, 1, omega 2, 2. Only that when you use orthonormal frames, these are equal to 0, and this is equal to minus that. But it's still a matrix, antisymmetric matrix like that. So the 2 by 2 anti-matrix using orthonormal frames, there's only one independent element in it, namely omega 1, 2. Okay? But in the general case, if you don't use orthonormal frames, then it won't be an antisymmetric matrix. We can prove that. Okay? And so there is, in fact, a matrix in there of if you're dealing with a tangent three-dimensional space, then the connection matrix would be a 3 by 3 matrix of differential one forms, in the sense that each element in that matrix is a differential expression of the first order. That's called a one form. Okay? In other words, each of those connection matrix elements, for example, omega 1, 2, would have to be some general function of x1, x2 times dx1 plus some general function of x1, x2 dx2. This is called a differential one form. Okay? So each of those elements is not a number, it's a differential form. It's a differential expression. Why? Because we are talking about small changes in here. Okay? And then if you have to divide it by dt, all you have to do is to stick the dt over here. Okay? You can't do that because the xi's, are, if you talk about a curve in particular, the xi's are parameterized functions, given functions of time. So you can imagine doing the time derivatives like that. And in fact, these things were what we call the script phi ij's in the classical mechanics text. And it's in terms of those things that the so-called angular velocity is defined. Okay. Okay. Now let's look at what happens in this case now. It's only one-dimensional. It's only one-dimensional vector space. So that matrix becomes a what? A number. There's only one element, the 1, element, so to speak. Okay. But if it's a number, we don't need these two indices, okay? And now in general case of a matrix, we introduced the so-called Christoffel symbols and wrote it like this. Those of you in my classical mechanics course will know. This is summation over k. So this is a general differential one form where each of these Christoffel symbols would be functions of the coordinates. Okay, in other words, specifically, ijk x1 through xn dxk. K is summed over, so there's ij in here. Okay, but when the fiber is one-dimensional, you can dispense with these and end up with just that. Okay? This is precisely what this is. With only one index that corresponds, that labels the different coordinates in here. In this case, 1, 2, 3. We're dealing with three-dimensional space. And in the sense that, these things are some functions of x, the x's, as are these general so-called Christoffel symbols. Okay? In the case of relativity, these things are four-dimensional spaces because the underlying space is four-dimensional Minkowski space, so it's a 4x4. The connection matrix is a 4x4 matrix. Okay? But in the case of ordinary non-relativistic quantum mechanics, this is a line bundle, so the connection matrix is just this thing in here, some function. Well, some differential. This is some, I'm sorry, the A's are just these things, not the whole differential, but just these coefficients, so-called Christoffel symbols. Okay? The whole omega is a differential one form, but these things are just functions. The Christoffel symbols are just functions. Now, why is this? You see, basically it's this, right? It's dEi dt is now omega ij ej. Okay, and now I can well, let me just write it like this first, and then let me get rid of the dt, so I don't divide by dt, so I have just that, like that. Okay. So in other words, without the dt, the covariant derivative, so to speak, is this thing in here, which is equal to some ordinary differential plus xi. And now, the thing is, now you can factor out, if these are two sums in here, so I can change j to I to j. And so I can have something j, I would be the same thing. And so I can factor out the EI like like that. Okay. And if now you write this as what? Gamma Ji dxj, like that. Okay? Now, if this is a one-dimensional thing, then there's no need for these symbols, right? There's no need for these symbols. There's only one thing in here. Sorry. K. But there's no need for the j and I, so this is just gamma k dxk. These are functions of the xi's in here, like so. But you see dxi, dx, whatever this is, well, that's what that is, basically, you know. And then you differentiate. You can imagine differentiating in here. Or in the case of a general, this is not xi. Let's say this is some general vector in here, okay? Some general vector in here. And so this becomes vi. Or in the case of one dimension, this becomes v. And v itself is some function of the coordinates, so you can imagine expressing the differential in terms of, you know, d dx, d dy, d dz, and so on and so forth, plus, you know, factor out some I in here, and then this thing is a v, so that's basically you have this thing operating on v ei, and it's this thing that corresponds to what we have over here. That's the that's the covariant derivative. It involves some ordinary derivative plus some function. And this thing in here, you see, in this case, the components of the vector potential turns out to be the Christoffel symbols in this case. Okay. Now, let me mention one thing before we quit today. This maybe takes a little bit of soaking in. Okay, you should go home and review that a little bit. This equation is not relativistically invariant, obviously not, because we're dealing with three-dimensional vectors and so on and so forth. And you'll see that it's not invariant under the Lorentz transformation, so in certain cases it's not as convenient to use as a fully relativistic equation. But there's an important invariance in it, which is called a gauge invariance. In other words, if you do a certain gauge transformation on the vector potential components, A1, A2, A3, and phi, the E and B fields will remain the same, even though you have undergone this so-called gauge transformation of the vector potential. But the Schrödinger equation itself will remain invariant in form under gauge transformation. So it's said to be gauge invariant, but not Lorentz invariant. And it's the gauge invariance part that we want to focus on at this point. I'll show you exactly how and why it is gauge invariant next time. I'll also show you next time exactly what kind of gauge transformation we are talking about. Those of you who were in my quantum mechanics class will perhaps remember that a gauge transformation just amounts to a choice of a different frame at a particular point, so that the connection matrix changes under that gauge transformation. In a similar way, all these A mu's will be different under a certain gauge transformation, but the important thing is that the whole Schrödinger equation will remain gauge invariant, and that's the important point that we wish to consider. Okay? All right, let's stop at this point.